In this video, I am going to go over Coulomb's law and the electric force. Now we are going to actually do not do any calculation in this video. I'm going to go over it kind qualitative talk about the equation, talk about the definition we have here and where the force derives from. So Coulomb's law, like most people, when they think equivalence law, they think of just the equation of essentially maybe definition might be that Coulomb law. Describe the electrostatic force between electrically charged particles. That means in order for this to be forth, the particles have to be charged, and you have to have two particles, and in this case we would have one positively charged particle and we could have one negatively charged particle. The one of the left you call particle 1 and the one on the right we will call particle 2, and they are not proton and electron, although it could be proton, electron, but it could be any charge. Object, okay, and we have charged objects, they will exert a force on each other. For example, in this case, they are oppositely charged, so they are going to attract to each other. This is positively charged particle which I have designed and this is the this arrow represents the force that this particle feels from this particle, and this arrow represents the force that this particle feels from this particle. Now, in this case, we have negatively charged particle and positively charged particle, just two particles. So the force they are going to feel going to be opposite in direction, but equally magnitude. Now the force is the force, and for the electric force is the force, and the force is the vector. So we show that graphically with an arrow, and the arrow has to have direction and magnitude. Now after times when we are drawing and we are going to these problems, we are not going to really be drawing the force to scale, but we want to show that it has direction. Now this force here, we are going to design it as F12, F4, a force 1, for it is the force on particle 1 from particle 2. So we say F12. Now we could say F21, the force from particle 2 on particle 1. But usually in most textbook, I think it would be F12 in the force of the from 2, and then will make the other on F21, the force on 2 from 1. So that kind of how we show the graphically, but how we think about it, design it with right, doing problem and making our sketch. All right, now could force have two positively charged particle, and then those two positively charged particles would repel each other. And of course, this is the force, this arrow, this vector force is a vector represent the force on number 1 from number 2, and this one of course on number 2 from number 1, and the same thing to go if we have two negatively charged particles, we have two force, they repel each other, and we would have F12 and F21. So that's how we kind of like to draw it. And we have a word problem. We usually make a little sketch, draw the particle, the force, and the direction. That the force are acting on those, and whatever force are acting on this particle. Now Coulomb's law, what's Coulomb's law? Coulomb's law is this equation force, electric, this is the force electric. Maybe it is different than the force gravitation force magnetic. This is the force electric, and we calculate the Coulomb's force, the force acting on charge particle from another particle. We have constant which we call K, and we are going to divide some stuff here, and the force is equal to K times the charge of one particle cube being the sample for charge, and times. We don't put an SI put but multiplication sign here, but it is the charge on one time to charge on the other divided by the distance between the two particles. Sometimes people put R here, R squared, the radius square. I like to put DD square divided by the square of distance between them. Now, the charge you use would be given, the other charge can be given the distance you will given, and K you need to maybe remember. Now, a lot of times you will get it equation sheet, but it is easily to remember. Just K equals 9 times 10, the tens of K. Usually it is just around like 8.99 or sometime, but usually just around 9 times 10s and 9s. Now it is important to remember that it has these 3 units. Newton, which is the unit of force, meter square, which is the unit of distance in Coulomb square, which is the unit of the charge. Okay, the Q stands for charge, but C is the unit of charge, which is the Coulomb from Coulomb's law. So now this equation tell us in this sometimes conceptual thing, it is a good idea to know the force on the particle is directly proportional to the magnitude of the charge. So that basically says if we increase the charge, the force goes up. If we increase this charge, the force goes up. If we decrease either charge, then the force goes down. But it is also the force is inversely proportional to the square of the distance between the charge. So you can see this is not just distance, this distance squares. So as the distance goes up, the force goes down. As the distance goes down, the distance between the particle goes down. The force is going to go, that should make some kind of common sense, because you increase the charge. Think of magnets, or this is the case, electricity you increase. The charge, the force goes up, but you make the charge farther apart. They are not going to feel each other as much. Now this equation, this type of equation is often referred to an inverse square law, an inverse square law, because it is inversely proportional to the distance. So this is the equation K, Q1, Q2 divided by square this radius square, and this is the K10 times 10 and me n times 10 to the times Newton meter square, Coulomb square. All right, now there is one interesting thing I think I would like to mention it. There are other inverse square law, and one of them you should be familiar with, of course, now, the electric force, but the other one you should be familiar with, the force due to gravity. And that interesting, we have two charged particles can exert force. The force of gravity is due to two objects that have mass and equations are very similar to each other. It is in the first case we have our constant K, and in this case for the gravitational force we have our constant G. Now this constant is a much bigger 10 times. I should remember, but this is like 10 to the minus 27. There is something because the gravitational force is much weaker than electric force. Alright, so then we are going to do some division, and of course we just said it is charge of one time. To charge the other now of gravity acts on two objects that have mass, so in this case it is going to be mass of one times the mass of other, and then we said earlier that this is square the distance. Well, the gravitational force is the same thing as square of distance, so the calculated gravitational force is gm1 m2 divided by the square of this disk. In this case it is kq1 q2 divided by square of distance. So you can see those are very similar to each other, even though the objects are very different. Okay, all right. Now the electric force can attract or repel, which is the difference than the gravitational force. The gravitational force can only attract, it is only attracts, the electric force acts only on charged objects. We don't use this to calculate this equation, to calculate the force of gravity or the attractive force on two objects, because their mass, we use it to calculate the electric force, and this is the gravitational force. Will act on all objects that have mass. So I think that just an interesting comparison. Maybe you are more familiar. We have talked about before the force of gravity being gm1 m2 square. Well, the electric force just kq1 q2 divided by square. So that in next video we will do some problem. This just a quick overview of Coulomb law and how we calculate it in this equation. Not really how we calculate